In our final Lab 6, we will talk about the Riemann sums and integrals. For the first part, the Riemann sums, our main goal is to be able to draw the graph, draw the rectangles representing the Riemann sums, and calculate the total area. And we will do that by creating two subroutines, one to create a Riemann sums using left endpoints and one using the right endpoints. So first, we introduce our usual libraries and the usual variable for SymPy. And now we will write our subroutines. So the first subroutine we will do is the left box. This will be Riemann sum using left endpoints. Notice it has 4 inputs, and the order of these inputs will matter, so we need to remember that. First two inputs, A and B, this is the interval on which we will do the Riemann sum. Third one, capital N, that's number of subintervals we will take between A and B. And finally, f is the actual function, and this will be the NumPy type of a function. So the first thing we do in our subroutine, we will set it up. We calculate delta x. We then get all of our endpoints, so our xi's. That means we will take interval from A to B, and we will take n plus 1 points there. It's n plus 1 because we have both A and B included for now. Then capital X and Y are just normal points to draw the graph of a function f. Now we want to only take the left endpoints of each subinterval. So we will take all the x's, but we will skip the last point, b in this case, so the rightmost point. We find their values, so y left, and we calculate the area of all the rectangles. So the area of one rectangle would be y, which is the height, times delta x. We will need to add all of them, but since all the delta x's are the same for each subinterval, we can just add all of the y values first and then multiply by delta x. Then we will plot. So we'll create our figure, we plot our graph in blue. Then we will plot each point x left and y left on that graph, and we will make them a little bit bigger so we can see them. And this is our rectangles. So we will use a bar chart here. So x left and y left are endpoints. Width is how wide is this bar chart. A line edge tells us what point should we use as the height of the bar chart. So if we use edge here, that means this x left, y left is the height of our bar chart. If we skip here, if we don't write anything for a line, it will use the middle point of each bar chart, which will be useful for your assignment. We have a title, so we will use a left Riemann sum, and then we'll write n equals something here. So when you actually create a title here, instead of these curly brackets, it will write whatever n is. So if I change the n, I will have a different number there each time. We draw our graph, and then we also underneath will print the area. So we already calculated what area is in a setup, so it will write the number. And we will also do the right box. It's more or less the same thing. There are only two changes that I need to point out. The first one is instead of using x left, y left, we're going to have x right, y right. And so notice I'm going to take the same lowercase x's, but in this case I will remove the first point instead of the last point. So I only will have the rightmost points of each subinterval. And the second thing I need to point out is the actual bar chart. If I just use x right and y right and rewrite the original command from the left box, it will use these 2 points as the left endpoints instead, which is not what I want. To fix this, I will use negative width. So notice my width is negative delta x. And so in essence, what it will do, it will use x right point as your height and end of your bar chart, but it will subtract the width now to create the actual bar. So x right is actually will be the right point. And the rest is exactly the same. So now let's look how this works. I will create a function minus x squared plus x. I will have an interval from 0 to 1, and I want to draw both left Riemann sum and right Riemann sum with n equal to 8. So it's 8 subintervals. So first thing we do, we create our function minus x squared plus x. I will have to lambdify it so that it's a NumPy function, and I'm going to call my subroutine. So first one I will call is the left box, so it's a left Riemann sum. Notice the order of my inputs here have to match the order of inputs I had. So the first will be a and b, so my interval from 0 to 1. Next one is the number of subintervals, capital N. And finally, my function, in this case it's fn. So let's call it. And here's my result. So as you can see, the title is left Riemann sum n equals 8. I have my graph in blue. These are my endpoints marked to make them look bigger. And then I have the actual rectangles, my boxes. So my first one has height 0, so you don't see it. The next one using left endpoint, the next one using left endpoint, and so on. And then underneath, we also have our area printed out. So this is the area of all the blue rectangles added up. Now we'll do the same thing for the right one. So it's just the right box subroutine. Let's call it. And as you can see, it is the same thing. Now we use the right most endpoints, and we can calculate its area as well. Finally, let's do this one more time using the right subroutine, but in this case I will change my n to 100. So as you can see, n is now 100, and this is what we have. As you can see, rectangles now filling up everything quite nicely. There's 100 of them here, and we can see now our area. It's 0.16665. So you can probably already guess that the actual area under the graph should be something like 0.1 and then 6 repeating, which is the same thing as 1 over 6. And now let's find the actual area underneath the graph. So we will use a SymPy library to do integration here. It's quite simple. So we will use command integrate. The first input here is the function. It has to be a SymPy type of a function. And then the second interval is actually a 3-tuple. The first entry here is the variable with respect to which we are integrating, so x. And then the next two is the interval. So we will integrate this from 0 to 1. If we replace this whole tuple with just x, then it will be indefinite integration. But in our case, we want a definite integration. Let's run it. And as you can see, we got 1 over 6, which was what we guessed. Quite often, these answers might be quite unwieldy, and so don't forget we can always use sp.n to rewrite our answer in a decimal notation. So here we go, 0.16 repeating. And the last thing we will talk about is how to do integration of polynomials specifically. This can be useful for modeling problems, for example. So let's say I have a polynomial 0, 1, minus 1. So this means I have x minus x squared. So it's exactly the same function I had. Let's see what it is. Then I can use the name of this polynomial, so poly.integ, and this will find antiderivative, so indefinite integration. So for example, in my case, this will be 1/2 x squared minus 1/3 x cubed. And if I want to then evaluate, in essence, have a definite integration, you will have to do it using the fundamental theorem of calculus. So subtract the antiderivative evaluated at 1 and antiderivative evaluated at 0. As you can see, we got the same answer. This last 9 is just, again, approximation error, so don't worry about that. And now let's talk about the assignment. Lab 6 assignment will consist of 4 problems. The first 2 problems will be very similar to the examples file. You will have to do the left Riemann sums and right Riemann sums. So you can reuse the same 2 subroutines from the example file, left box and right box, just copying them over. And this should not be a very difficult problem now. The problem 3 will be about midpoint Riemann sums. So you will have to write your own subroutine here that will do the same thing as left box and right box does, except using midpoints now. You can reuse the left box, for example, just change few things. Specifically, you will need to change the way align works. But for the most part, not many changes needs to be done there. And finally, the problem 4 will be a modeling problem. So you will have to do certain modeling, plot the graph of a model, and then integrate this. So here you can use the polynomial library to integrate.